Hi, my name is Martin. I'm here to talk to you about some interesting tidbits and some lessons that I learned from optimizing .NET code. I work for Tieto in Austria, so in the next big tower over there. I work as a software engineer. I do contribute a little bit on GitHub, and that was actually very helpful because actually Microsoft engineers helped me a little bit in optimizing my code, and some other people stepped in on Twitter because I was able to open source a small part of the thing that I was working on and get some feedback of people that really know how CPU level instructions work. So that was interesting, and what I want to share with you is talk a little bit about performance, run some benchmarks. Hopefully this works, because you should never benchmark on a mobile machine while giving a presentation in a virtual machine. So we'll see how that goes. And I want to talk to you about code and optimizations, and actually very low-level optimizations. And when we think about performance, I'm mostly talking about processing data. So if you're shuffling data streams around the networks, maybe your use cases will be different. But when I talk about performant code now, it's mostly about processing some forms of data. It could be text, could be interactions that you need when you're doing data science or machine learning. So it's always interesting when I talk to people, especially Python developers, to tell me, yeah, my Python function is great. I mean, I know Python is slow, right? But Python just calls C APIs, so the C code will be fast, right? So they hope that their C libraries save them. Others say, yeah, but for big data sets, I use the GPU, of course, because the GPU can do a lot of things quite fast, especially if I'm doing parallel processing. So that's a good way to go, right? Well, yeah, I think GPUs are a good way, but the problem is always we have to move data between the GPU and the main memory. You may not want to process like every HTTP request, like a stream of data on the GPU when you're just looking for like line breaks and semicolons and stuff like that. So you really want to get all the native benefits that you can get from modern processors. And one of the tools that can do that is actually C and C++ compilers. So what C++ compilers can do is they look at your code and they try to find out what you were actually semantically doing in that code. So if you're writing a for loop, it may actually write some interesting code dependent on the hardware that you're using to generate platform-specific code and use very specific instructions to do things like summing up code or finding some values in a big data set. So this is called loop vectorization, and it's a very interesting topic of research. Sadly, .NET cannot yet do that very well, but our JIT compiler that we have in .NET actually generates quite good native code. So if you are implementing simple functions, we should get about the same results as a classic C compiler without any loop vectorization. So hard intrinsics are about moving .NET Core to the next level to be able to use all those platform-specific features. So why do we want that? Because our hardware can do a lot more than you probably think it can. So the base instruction sets that we're using are quite old. So the x86 instruction set is like 90s something, and there are a lot of extensions. So when you look at a modern CPU, you see, oh yeah, this is an x64 CPU and it can do all of that. Yeah, right? So it's very helpful to have that list if you know what these things are. I'm going to talk a little bit about some of them. The interesting thing is, while in the Intel space, we're mostly having extensions to the instruction set. ARM actually versions their instruction set. So there's like ARM 6, ARM 7, ARM 8 is now 64-bit, and then there's like 8.2. I think we're now at 8.5, something like that. And but there are extensions as well, and that's interesting because mobile platforms usually they're built for some purpose, so they may have specific CPU extensions or co-processors for that purpose. So if you're doing multimedia, you might have some other capabilities than some measuring equipment. So that's interesting. Also, when you run Intel CPUs, you can use the CPU ID instructions. So like you call an instruction in assembler code and the CPU will fill the registers with basically, yeah, I can do this and that and that. Whereas in ARM, only the kernel can do that. So it's a bit more interesting to set up the calls like can run that code or that code that has to go through the operating system. So it's a little more complicated. But those are all there, right? So what do I do when I figure out that my code is slow? Yeah. First of all, profile. Gather data. Personally, I use .trace to find out where I spent my time in code. And of course, benchmark. Like write some test codes and repeat. Forever. Then, what would you do if your code is slow? First of all, try to do everything that .NET offers by default. So maybe look at your memory allocations. Maybe you're spending a lot of time garbage collecting. Like I've seen image processing libraries that basically spend a quarter of the time basically sleeping and waiting for garbage collection because they were allocating new buffers to process images. And it turns out that's quite slow, especially when you're trying to have a live preview of the thing that you're looking at. Maybe if you're using libraries that wrap data, like metrics libraries, there may be some layers of indirection for accessing data, which is quite bad if you're trying to process data. So in my case, I was using MathNet numerics, and it turned out to be much faster to just use an array of numbers and index into that, or have a single array instead of an array of arrays, like multidimensional arrays, because that's actually a little bit slower than just calculating an index into a big data store. So those are things you can do. If you want to write performant code, also avoid link at all costs. So link is very, very bad performance-wise. I think link is very good to improve like readability and bring down maintenance cost, also build some compositional logic, but it can be really bad performance-wise. So it depends on what you're doing. You may need to find a balance. But especially if you're doing like sum, max, minimum, averages, etc., without any predicate filters, you're really wasting time in there. So what you would then be looking into, if all those things don't work, is look at ways that .NET can help you vectorize your data. So process more data at once. This is where things like system numerics come in. So that could be helpful, or investigate like other data structures that you could use. Like if you're trying to find something in a database and most of your calls come back with not found, maybe try using a Bloom filter. Maybe look into bit arrays to maximize the storage capacity. Look at B trees, something like that. There are a lot of data structures that may help you address your problem quicker. So, but if all that fails, then look at the hardware. So, what can the hardware give you? The hardware can give you single instruction, multiple data operation, which means you have an add instruction, but I want to run that add instruction on 16 shorts or 32 bytes at once. And modern CPUs can do that. And so what this means is you operate on vectors of data. And depending on the processor you're using, this vector can be of different lengths. And this has quite a history. So I think Intel started with multimedia extensions back in the 90s, late 90s. And this was basically 64-bit operations on some integers. Remember that this was in the time 32-bit computing. Then we got the streaming SIMD extensions. Actually, AMD was first using the 3D Now extensions, but then Intel standardized the SSE instructions, and AMD also implemented them. And they gave you 128-bit registers. So you could have 8 registers that could hold 128-bit, which would be divided into the things you would be processing, like 16-bit floating points, 32-bit floating points, etc. And this SSE is still around. It's been revised a couple of times. There's SSE 2, 3, and so on. But the latest edition is the set of advanced vector extensions. So AVX gives you 256-bit registers, and actually 16 of them. So you can store more data, process more data at once, and it also has more capabilities in the sense of the instruction it provides you, like gathering data from some other pointers, and there are even some masked operations now, and of course some interesting fused multiply add instructions that you can use for mostly for processing matrices and doing matrix operations. Then there's AVX 512. This is the latest one. Intel started shipping processors in 2016 with Skylake, which now gives you 512-bit registers, and actually 32 of them. So the CPU can now hold 2 kilobytes of data and operate instructions on them quite fast. So quite a powerhouse, but there is a catch, because when you run AVX instructions, the cores that run them will actually become slower. So they slow down the clock rate of the core, but they're still able to process data a bit faster than you would normally do. But in the 512-bit version, there was a bug where if one core ran AVX 512-bit operations, it would slow down all the cores, which is pretty bad if you have like an 18-core machine. You would run AVX instructions on one of them, and now your whole process gets slow. So I think that is fixed in the 2019 Cannon Lake processes, but I think Cloudflare tried to port their SSL, like TLS implementation, to AVX 512, and they figured out that they actually get less throughput than with AVX2. So let's see how that goes. So what else does the hardware offer? There are also interesting smaller functions that help with a lot of common use cases. So especially if you're dealing with bits and some integer data, there are a few helpful operations like a trailing zero count, like how many zeros are in the right, so the lowest bits of an integer. This will come in handy later. And there's something like and not and some other logical operations that you could just execute instead of executing 2 or 3 logical operations. So also, if you want to know how many bits are 1 in an integer, there's pop count, or there's also trailing zero count, leading zero count, like a lot of interesting things that you might not need all the time, but when you need it, they're quite fast and easy to use. So how would you use all that stuff in .NET Core? So .NET Core has actually 2 use cases, 2 APIs for that kind of stuff. One of them is system.numerics, and system.numerics provides a few built-in classes. One of them is vector of t, so you can create a vector of ints, a vector of floats, vector of double, etc. And the length of the vector will be dependent on the platform you run on. So if you run on AVX2 machines, you will get 256-bit of data in 4 vectors of t. But there are also specialized types like vector 2, vector 3, vector 4, and matrix 4x4 that can help you with small amounts of data, which is very interesting if you're doing graphics processing for storing color information or positional vectors. And that's quite useful. And vector 2, vector 3, vector 4 work on all platforms. Vector of t does also. It may just fall back to using 4 variables and thus 4 registers in the CPU and not the SIMD versions. This is also what you get in .NET Framework, so you can actually use this as a NuGet package for .NET Framework. I think it's also built in 4.7.2 or 4.8, but it will be slow unless you're running .NET Core, which will hardware optimize the things that run on top of system numerics. But in .NET Core 3, actually this was introduced experimentally in 2.1, but is now fully released in .NET Core 3, is a new system runtime intrinsics namespace. And this is where the juicy bits are. So this basically directly exposes all the things that the hardware can do directly to .NET functions. So you can call leading zero count on an integer right there. You can directly address vector registers, not the individual registers, but this is actually a very, very nice API over the things that the hardware can do. And I'll show you some code later, but it's very great, but there is no software fallback. So if you're not running on a machine that supports this specific instruction set, you need to check this with an if. So you would drive if avx2 is supported, then run the fast version, else software fallback. Maybe check for avx, then avx2, avx, maybe run some SSE code instead. There is no version for ARM at the moment. ARM is being worked on because it's more complicated to find out which features are actually available, and the feature set is more diverse, but it's being worked on. But the interesting thing is this was actually proposed by Intel, and also contributed, a lot of the code and the API was contributed by Intel and was implemented by both Intel, the community, and Microsoft themselves. So that's very useful. Okay, I think I copied something there. Yeah. So when you're using this, be sure to always implement fallbacks. And if you need to test the different branches, there are environment variables that can tell the JIT compiler, like, hey, okay, this machine would be able to run it, but just turn it off for now and see if my unit tests still run. So this is useful if you need to test this. Also, the code is unsafe mostly. What this means is you can write code that will kill you. So maybe stress test it, especially when you're writing code that is optimized for accessing data at specific points in memory. I will show you that later. Because if you're using managed memory and you pin memory and you use unsafe code to work with it, things can go wrong, and you can't really predict where the .NET gauge collector will allocate. Yes, the gauge collector is actually the one that allocates. Will allocate the memory, and if you try to optimize where in the thing you're working, and you do that wrong, you can crash. So please stress test your code. But then it's going to be fine, right? So why would I want to do that? Well, first of all, it's good to know that the things are there, and they're actually already used by internal functions inside of .NET Core. So if you're using spans, like you should all be using spans, and you have, for instance, a span of bytes, and you call index of or index of any, this will go to span help, and this is actually implemented using avx2. So this will actually be very, very fast on .NET Core 3. So another reason to upgrade. This is also used by ESP.NET to tokenize requests. So if you have a span of char, you can also use index of any to find new lines or semicolons. Yeah.
Can you say what span is?
Span. Okay. Span is a representation over contiguous memory. Okay. So a span will always refer to some form of memory. That could be native memory that is used from some C library that you use. Could also be based on strings. Then it would be a read-only span in most cases. Could also be based on an array. So you can call array.span, and then you get a span that has that is indexable. But you can also create subspans, and the span is also a struct. So you're not copying data, you're referring to data. So if I were to implement quicksort, where you like divide arrays or something, you can do this using spans and not copy stuff, and still have a reference to maybe a part of an array, and pass that around. And it can only live in a stack, and it can be created from various interesting parts of memory. So I think you can even use stack alloc to create a span, which don't do in production if you don't want to get security issues. But that's interesting code that's usable, and it makes .NET Core 3 fast. So I'm hoping that more of the data structures that we use will start making use of those APIs. And also machine learning, ML.NET, now uses these intrinsics to make machine learning models execute faster. But you could also use it yourself. So if you're building libraries, there's ways to use it. So why am I talking to you about it? Does it make a difference? So my experiences, I was implementing an algorithm that's called the Kuhn-Munkres algorithm, also the Hungarian method, Hungarian algorithm, which is an optimization, a linear optimization problem solver. So it tries to find a global lowest cost for an association problem. So of course I do that every day. So the thing that I tried to solve, just to illustrate, is I have it's not my use case, but this is the Wikipedia use case. So you have contractors that submit offers for 3 different types of work. And the idea is you need to contract all this work at the top to any of the contractors on the left. And you want to do this in a way that minimizes your global costs. So if I would run this algorithm, it would tell me use these assignments, because these assignments will have the least overall costs. So there are other applications as well. One of them is from radar tracking. Like if I track airplanes on the radar, like the airplanes will see the radar, will see. Does that work? Oh, okay. I see that pointer on the output, yeah. So it sees 2 airplanes every time it scans, and then it gets 2 new dots. But the tracking algorithm usually tries to predict where the airplane is going to go. And if I would just associate the points on the radar with the prediction that I have for where the airplane would be, I maybe would do an assignment that would not be a global optimum. So maybe I want to assign this airplane to the point that is actually near the predicted point for another airplane, and move the other airplane down to another point, instead of maybe discovering a new airplane, to just recognize, oh, there has been a movement. Another way this is used is for computer vision. So when you're doing tracking for computer vision, this is basically the same problem. You recognize objects, and then a few frames later, you recognize objects again, but maybe more, maybe less, maybe they've moved. And you make decisions of, do you move your tracking objects, or do you create new ones, or do you recognize, yeah, something has left? So this can also be done using this algorithm, because you usually have some form of cost representation. I think it's also used for matching riders for ride-sharing applications. So if you have cabs waiting around, drivers waiting around, and people on the apps requesting rides, you usually want to have an association that makes all the people happy. And maybe this involves someone that's right near a person that wants a ride to like drive a minute to the next one, to avoid someone having to wait for 10 minutes. So interesting applications. But of course, it can also help optimizing purchase decisions. And I think it can also be used in factories, like matching up parts with minor defects, or creating a product that is best based on individual measurements of different parts. So that's one of the things that they can be used for. So The interesting part is it will find a global optimum if there is one, and it solves the problem in a predictable polynomial time. So if I know the size of my problem, I can predict what's the maximum time is that it's going to be solved in. And this is very critical for industry applications. But the problem is time is n to the power of 3. So this is not very good, but still it's a good algorithm. So could I make n to the power of 3 pairable? So can I optimize it as good as humanly possible to be very, very fast? And this is exactly what I did. So I started benchmarking it, found out that, of course, if I use a library that also has some allocations that tries to create a matrix, this is okay for the most part, but not for this algorithm when I want to like call into the data and like subtract some values from each other and keep track of some locations. So I replaced it with arrays. I also moved from doubles to floats because single precision turned out to be enough. I wasn't quite comfortable converting to integers because I couldn't really predict the scale of the values coming in and also the relative scale. So I used floats. And of course, I used a float array, which was faster than, and this should read a multi-dimensional array. So if you use a single-dimensional array, or at least not an array of arrays, which I had before, this was very fast. Also calculating the index myself, and thus calculating my own, I think it was a column major storage over a float array. And this turned out to be very fast, and it also already reduced the runtime cost by 50%. So it cut the runtime cost in half by just using regular benchmarking techniques. But then I wanted to test hardware intrinsics, and I looked at the profiler and found some hot paths and tried to use advanced vector extensions on them. And what I found is that I could reduce the overall runtime to 10%. So from the initial 50% cut, I was able to optimize another 50% completely away and make it as fast as possible. And the way this looks is this. So in the, sorry. So in this one is the original implementation, which is super slow. I mean, I tried to run it in different problem sizes. So this is a benchmark graph generated by benchmark.net. And you see, yeah, okay, for small sizes, I think the red one you don't even see, so it doesn't really matter. But for large problems, it was taking over 3 seconds. So quite a long time to run. And then the next step is I moved floats, and then I removed the system numerics dependency and made sure I had the best possible .NET code. So this is in half. And then I did some steps of using AVX to reduce overall costs. And this is where I ended up. And it's not even perfect, but good enough for my use cases. So this actually made it possible to use this algorithm in our case, because we didn't have to wait seconds for something to complete, but just a few hundred milliseconds at most. So it made O of n to the power of 3 bearable. You can also find it on GitHub. And of course, I spent a lot of time on this page, which shows all the different things that I could call. Like if I want to find out what is the maximum value in one of those registers, yeah. There are a few things that are interesting. One of them is for every type of argument that I'm using, like this one is for 32-bit integers, signed integers that is. The PDs are used on a floating point, etc. Those would be very hard to find, right? So actually what .NET does is it offers us better API that will select a different method based on what we actually pass as parameters, because we have method overloading in .NET. And C doesn't. so they need to change the name. But the interesting thing is, for most of the methods, they have a measurement of the latency, how long will you wait for this command to complete, and what's the actual throughput. And if the throughput is lower than the latency, the CPU can actually try to run some instructions in parallel. So we can also take advantage of instruction level parallelism for vectorized code. But there are some, where the latency is just abnormal. What is that? Multiply integers with producing intermediate integers and store the low 32 bits in somewhere. Yeah, so they're very specialized use cases, but they're helpful. So if you're interested to find out what you can actually do, this is the guide to read. So, and the code that I want to show you is a small demo for adding numbers. But I want to use vectors to add numbers and add numbers fast. So when I'm talking of adding numbers and trying to make something fast, we want to run benchmarks. I've set up benchmark.net here. And what we have is we have a values float array that is filled with random numbers. And we're starting out with very naive code. So the baseline is going to be a very naive sum. So we're just having a for loop that iterates through the array and just sums up all the values. And also let's just compare it with the link version, and the link version would be just sum the values. So I have no idea if this is going to work in a VM inside a presentation, but let's try it. I've also marked it as a short-running benchmark, so the results are maybe not that accurate, but should give a hint of how they are comparing. So the naive version took 143 microseconds, and the link version, 4 times as long. So I told you, don't use link if you're doing very simple things and want them to be done fast, but use naive code instead. It will usually be fast. So the next thing I told her is, okay, if you want to do vectors and you don't want to touch unsafe code, use system numerics. So system numerics provides us with a vector type, and here I have vector of float. So what I'm doing here is I'm trying to sum up all the values that I can as vectors, but of course there is a vector size dependent on the platform, and my data may not be a multiple of the vector size. So let's just calculate how many vectors I can use for summing, and for all those I use a span in this case, because from a span I can slice the specific vector size that I can use. This is allocation free, and a vector can be constructed from a span, so I can just create a vector from my data and add it to my temporary data. So far, so good. Okay. Okay, so I'm just trying to calculate how much of the data is a multiple of my vector length. So if if I have 12 elements, but a vector size of 8, I cannot use 2 vectors of 8. I have to use 1 vector and then handle the remaining ones specially. So what I'm doing here is I'm creating vectors for all the things that I can put inside a vector, summing all those vectors together. And this is already using the best method that's possible on the platform, just behind .NET APIs. So the JIT compiler will take this and optimize this based on what machine I'm running this on. So this is actually very, very useful. But I'm still having a temporary vector. So what I'll do is I'll just sum up the values inside a vector. I can use the vector by indexing. It behaves a bit like a normal array. So for the vector size, I'm just pulling out all the individual values. So In our case, this would be 8 elements, 8 floating point values. And then I handle the rest of the values. So I think I instantiated it with 100,003. So it should handle the remaining 3 items, because I can't fit 3 items in a vector of 8, because I would access memory that's not part of the last elements. So this is a lot more code. How fast does it run? Maybe I should have started that before.
You also make sure that you get the right result.
Yeah. I have some backup results.
Yeah, because that's the major.
Yeah.
I mean, I understand.
Yeah. So, in order to do that, I actually created unit tests inside this to test all the different methods.
Excellent.
So, I made sure that the values are correct, because for the unit test, I just fill 1 inside them and just test if it's the same, if it's the length of the vector. So, I'm testing that. Yeah. Always test the results. And okay, what are the results here? Yeah. It only uses 13%. So I'm taking 21 microseconds instead of 160. So yeah, nearly an 8% or some 8 times improvement. So that's actually quite a lot. But I told you there is a different API that you can use. So what happens if you try to use that? So we have the advanced vector instantiations, and let's uncomment those. And for these, I have to use code that you should always test and get a few people to review, because it is unsafe. And what unsafe means is you have to configure your project file to allow unsafe code, which is similar to when you go to the doctors and you need to sign a release form to get very, very strong medicine. So it can help you, or it will immediately kill you. So this is fun, right? So I'm doing the exact same thing that I was doing before, but I first need to check if you can actually use AVX, right? Because this could throw up when you try to run it cross-platform on an ARM machine or a very, very old computer. It may not work. So after this if, there is a fallback. But inside this if, I'm doing the exact same thing as before. I try to find out how much of my data I can actually process in vectors. I create a temporary vector, but now I use a different type. I use vector 256 for 256 bits of floats, 0. And then I'm doing crazy things. So then I'm going unsafe to enable a lot of interesting compiler features. And then I'm using fixed to get a pointer to the first item of my array. So C# can use pointers. Yeah. They're unsafe, they can kill you, but they can really do a lot of things. So I'm having the same for loop as before. For each vector in my set of things that I could vectorize, I'm using AVX, load a vector, and here I'm doing pointer arithmetic, which is fun in C#, because if I'm using pointers of float and I add values to them, it will increment the pointer by the size of the type that it's referencing. This is very useful. This is a bit safer than pointers in C and C++, but it's still dangerous. If you get that 4 wrong, the program will just exit. Like, there's no way to recover. There's no exception you can catch. It will just throw yet bad access. Goodbye. If you're lucky, you get an execution engine exception that you can't catch. But you can use AVX load vector 256, and then you can say, okay, the temp vector will be avx.add the temp vector and the values vector. So I use my temp vector and add those new vectors to it. And actually, I showed you the big scary list of instructions before. This actually tells me which overload I'm actually using, and I could look up this method in the Intrinsics guide. But because I'm passing in vectors 256 of float, I get this M256 thing. I also get PS, which is single precision floating points, and the right add instructions for 256-bit integers. So I don't have to use the scary method names. I get very fancy named methods from .NET.
So the
Yeah.
function adds all the values inside the vector.
Inside the vector, exactly. So I have 8 floating points in that one, and 8 floating points in that one, and I just calculate the sum, which gives me another vector with 8 elements. And after that, I exit unsafe code, and then I do the same thing as before. For those remaining 8 elements, I take all the elements out, put them in my sum, and then I handle the remaining, in our case, 3 elements that I couldn't fit inside a vector. And now, this code looks very fancy, but remember, when you use fixed to take a pointer to manage memory, the managed memory will be pinned by the garbage collector. So if a garbage collector is running, it may have to move memory around the fixed memory, and it may make your program slower. But if you're operating on large sets of data, this is actually a benefit. So there are ways to use AVX without using unsafe blocks, but you still have to use references and unsafe.add. And if you want to go really deep, which we're doing in the next one, this also wouldn't work. So what are the results here? So numerics now took 19 microseconds and AVX 18. So not really a good improvement. So the performance is about the same, because actually system numerics is a very good wrapper around AVX. And if you're doing something like add that it provides, you won't have any problems. If you're doing intrinsic, fuse, multiply, add stuff, system numerics may not help you, then you have to use this method. But system numerics is very good. But what more can we do? So there are more features that the CPU can do. And in this one, I'm actually doing 2 of them. One of them is called pipelining. So if I have a large set of data, it takes a bit of time until my vectors are loaded from memory to the vector register. And then if I do some calculations, then I load again. This can take some time waiting for data. So if I put more load instructions after each another, the CPU can actually reorder the instructions to make them faster, because I can load memory while I may already be calculating the next values, or it can just be faster because the pipeline processor already knows which parts of memory to prefetch. So it can be faster to maybe process 4 vectors of 8 float points inside a loop. This is called pipelining. But the more interesting stuff is memory alignment. So this is the most interesting part, and actually the most complicated one. Because when we have memory addresses, those usually get incremented by 2, 4, 8, something like that, depending on your platform. So if you request memory, you get an address starting at some point. The thing is, AVX is actually super fast when you're loading vectors from a memory address that is a multiple of 256. Because I don't know how exactly this works. I think the registers are hardwired to the cache, but it's really, really fast. So if I want to take advantage of that alignment, I first need to find out, okay, I have some managed memory. Am I on a 256 byte boundary or not? If not, I need to process some elements individually until I hit the boundary where my memory address is a multiple of 256. And from then on, I can use vectors until I hit the point where maybe my pipelining doesn't work anymore. Then maybe I have 2 or 3 vectors left. And then I need to process the last elements that can fit into a vector. And if I do all of that, I think you can read the code later if you're really interested. There's some interesting code in here to find out how many elements I need to process until I hit the boundary. But if I do all of that,
already here.
Oh,
You need to talk properly.
Or maybe I can ask a fundamental
Yeah.
question in between. So when you say 256
Bits,
bit
yeah.
thing, is there kind of like the CPU is 64 bits?
Yeah.
Where does the thing, but it has some separate hardware.
There is separate
next
hardware
to it, which has these long.
which
registers.
has long registers. Yeah.
Okay. Yeah.
So if you're running an Intel, you have 32
Of
512-bit
these
registers.
extra
Yeah.
registers. Okay.
But as far as I know, there are no instructions that use more than 64 bits at a time. So you could use, for example, AVX2 with 256 bit registers to store like 4 integers next to each other.
Right.
So if you're doing splitting data, that's interesting because you also can reinterpret the data inside the registers. But or you can store 4 32-bit floating points or integers. So there are various ways to use those registers.
Right.
And there are also instructions to like load 64-bit and then move it up. Like if you want to convert your 16-bit integers to 32-bit integers, you can do that. And there are a lot of instructions. But as far as I know, there are no 128-bit or higher instructions to use.
But kind of, it could be tricky if I say I put 4 integers into one of these registers and I add them. If one of those registers, one of those numbers creates something like an overflow, the memory has to.
Yeah, no, the memory will stay in that boundary. So it will split the data into processing units that are lined in parallel, so they don't interfere with each other.
Okay.
And not overflow in these memory areas.
But how does the CPU know that those are 4?
Because it interprets the instructions.
Okay.
And the way the hardware works is so that it basically copies it again to a temporary processing unit and then copies it back to the specific registers and won't crash, hopefully. But it's interesting because there are some operations that where they look at the data next to each other, so like a horizontal add. And there are some limitations, especially when you're using 256-bit operations. There are some operations that can't go beyond the 128-bit binary because of hardware limitations, like to which processing unit stuff goes. Like there is one operation as a specific shuffle operation where I can shuffle the bytes around. I used that when I tried to determine the minimum number in an array, where I just took a min of all my data and then shuffled data in the vector and used min operations to reduce the numbers of min values inside my vectors until all the elements were my minimum value, and then just use those. And you need a very specific shuffle instruction for the first shuffle. So lots of stuff that you can do. So our memory boundary optimized pipelined version took 8 microseconds instead of 18. So we reduced our 3-line for loop, 2 of which were closed brackets, to 5% of its original duration. So I think this is kind of very impressive. Maybe you will never have to do that yourself, but everything that uses math on .NET Core 3 can take advantage of this performance. There's another one I'll just show you, which is if I have a set of values that are maybe growing in value, and I want to find the index of the first value that is greater than some threshold. Like you can use the same logic to find like where does my function hit 0 or something like that. Like there could also be a simple for loop that iterates over all values and returns the index. Then I've seen a lot of people using LINQ to implement an index of the first element that is greater than the boundary. Yeah, I've seen this extension a lot of time in code, and it's not bad for scanning through objects and evaluating things, but maybe not for calculating. And of course, an AVX version. This time without memory alignment, just to make it some form of readable. But what I'm using there is I create a vector based on my limit value. And then for all the vectors in there, I load the vectors of things to compare. And then I can use an AVX compare function where I can tell me, yeah, compare my values to my limit with a greater than or equal. And there's also interesting configuration options. These ordered and non-signaling values are can tell the processor how to handle not a number values. So this is very interesting if you're doing data science and you need to handle not a number value, and you want like less than or greater than have a specific not a number handling. This is very useful because if you try to use like min or average link functions in .NET, you may have interesting results when there is a not a number value in there. But so what the comparison result is, it just sets all the bits to 1 in the parts of the vector that match and the other ones to 0. So I have maybe a 0, 0, 0, 0, 1, 1, 1, 1, 1, etc. But there is an AVX function called moveMask that basically takes the first bit of every part of that vector. So if I'm using a vector of floats, it would be it would take 8 of these bits and move them into an integer. So I get an unsigned integer with a few bits set. And if you remember, there are interesting bit operations. First of all, if the number is 0, I didn't find any match. If not, I can use the trailing 0 count to find the offset in my vector that first matched the comparison and just add them to my index in one instruction to find the location of the thing that I'm searching for. So I can talk about this in more detail later if someone is interested.
Did you say that your values were stored?
Yeah, just to get the benchmark correctly every time.
Oh, because I would use binary search.
Yeah, of course. Binary search is a lot better if you're searching in sorted data structures. I think I've heard people talk about even using it unsorted data because if you split it correctly, you can get a more consistent behavior. But so, and if you I should have run the right benchmark, right? I'm actually quite surprised that I get consistent results inside a virtual machine while presenting.
So those CPU instructions are actually kind of piped through the virtual machine, which knows these instructions.
Yeah, but exactly. But since Intel implemented CPU extension for virtualization, called VTX and VTD, this actually has a very low performance impact.
Yeah.
So, the naive version, 77 microseconds, link 11 times slower. And yeah, AVX just 9 microseconds, and again about 13% of the original load, so a lot faster. And yeah, you can find this on my GitHub. I do not have the link in the presentation. But again, short recap. Do performance optimizations. Don't use link if you want to be fast. Try using system numerics, and if that's too slow for you, look into hard intrinsics. Questions? Okay, then thank you very much, and I've heard that there is pizza outside.